Hello, welcome to this presentation titled How to Make a Transparent Laser. I'm presenting some thoughts on a common challenge in laser development and on computer modeling as a powerful solution. You hear Rüdiger Paschotta, the founder and executive of RP Photonics. First, I would like to tell you shortly what I mean with the design of a laser product. The design is what defines what components are used, where they are positioned, etc. The images here show you some examples, of course not containing all the design details like data of the used components, their spacings, etc. Such a laser design is actually always based on more or less detailed mental conceptions about internal phenomena, like pumping of laser active ions, stimulated emission, saturation effects, propagation modes, etc. Ultimately, any laser design must be proven to work in experimental tests. You have to build the laser, operate it, and check what comes out. Experimental tests, however, can often reveal only to which extent the achieved performance is as desired. But essential questions may stay unanswered. For example, why is the performance so poor? What goes on inside the laser device? What is the cause of some observed strange behavior? A basic problem of lasers is that you cannot look into a laser crystal, an active optical fiber, a frequency doubler or whatever component in order to see what happens inside. You cannot even put your power meter or beam profiler into an airspace in a laser resonator, even if geometrically there would be space for it. The laser actually behaves like a black box. You can analyze only what comes out, but not what happens inside. And this problem is actually quite typical for many photonic devices, but it would be different for electronic circuit boards, for example. There you may easily probe voltages at various locations. The essential differences are that light fields other than electrical signals in wires can have complicated spatial structures, and they are strongly affected by the presence of diagnostic means. Now the trouble is, how should you be able to fix problems in a laser if you don't understand their causes? And also if you don't understand what the effects of possible design changes are. Should you use only trial and error? Well, let us imagine for a moment that you would build a laser from transparent components, where you could simply look inside and see what happens. So, for example, you could see what are the optical intensities at any location with a micrometer resolution, and at any time, with a nanosecond or even femtosecond resolution, inside your laser crystal, your fiber or your frequency doubler? How does the beam quality of the laser radiation at any location evolve during the pulse buildup? And how does the excitation of laser active ions evolve? Well, that would of course be marvelous. Finally, you could find out what exactly happens inside your laser and how to fix any problems. But isn't that just a dream? After all, where can I buy such components? Well, I have some good news for you. You can indeed make whole lasers and even more with all transparent components. I will tell you that in the following. The basic trick is that you create a computer model of your laser, which contains a simplified description of the device, with details like length of your active fiber, doping concentration in the fiber core, transition cross-sections of the active ions, the properties of seed pulses which you put in, etc. Then the computer model simulates all essential processes. Based on that, it calculates the observable performance, and finally it nicely presents all results, observable quantities as well as any internal details, for example as numerical values or in graphical diagrams. What you need for such a computer model is, first of all, an ordinary PC. I suppose you have that already. then some suitable simulation and design software. The third is data of the used components. And finally, a decent know-how and/or competent technical support in order to do things properly. Let me give you a few examples of what aspects you can treat with different kinds of software. For example, if you have a powerful fiber optic software, such as our product RP Fiber Power, you can simulate pump absorption and amplification in an active fiber, do numerical beam propagation, for example, including bending effects, simulate the amplification of ultra-short pulses, including effects like chromatic dispersion, nonlinearities, etc. And you can use all that to learn how fiber lasers and amplifiers really work and how to develop optimized designs for them. Another example is laser resonator design. So if you have a powerful resonator design software, such as our product RP Resonator, you can calculate any properties of laser resonator modes. Most importantly, you can calculate mode sizes, for example in a laser crystal, in a frequency doubler, or on laser mirrors. Then their sensitivity to thermal lensing effects and to misalignment. And you can use all that to learn how exactly laser resonators really work and how to develop optimized designs for more output power, better beam quality, lower alignment sensitivity, and so on. A third example is if you have a pulse propagation software like RP ProPulse, you can simulate how ultra-short light pulses evolve in mode-locked lasers, in amplifier systems, in parametric oscillators, etc. And again, you can use that knowledge to learn which operation regimes are stable and on which parameters the stability and also the performance depends. Well, it is very obvious that a tool telling you what exactly goes on in your lasers or amplifiers or other optical setups is extremely useful. It just ends your blind flight and allows you to understand and fix problems in an efficient manner. In the following, you will learn more in detail how to utilize such a model in practice. For example, for developing a good prototype design, for understanding your real laser even if discrepancies occur, for working out your final product design, and for resolving problems with unexpected behavior. Let me begin with the development of a prototype design. Before ordering any real components, which of course costs a lot of money and waiting time, work out a prototype design on your computer. That means you describe your conceived design in the software and get its performance simulated. Now you can first thoroughly check the results. Are the performance goals actually met by your design? Are all parameters in safe regions? Are some of them perhaps excessively sensitive, for example to alignment? And if unexpected things happen in your model, just look into the laser model to see what happens inside. And if you encounter any problem, you will understand it for sure after a while. In difficult cases, you just use the technical support. You can then revise your prototype design as needed until you arrive at a well-working prototype design. Note that all this can often be done within a single working day. Now it comes to testing the design in the lab. Well, first you can order your real components. You now know what you need. Then you build your prototype in the lab and test its performance. If it works as expected, well, that's great, then you have done a big step forward. Also, you know that further tweaking of your prototype makes no sense because it does already realize the potential which is defined by your design. But if the performance is not as expected, which may happen, or some unexpected behavior is observed, then you can do the following. First of all, check whether the real laser really matches your planned design. For example, have possibly any laser mirrors been mixed up? For example, used wrong curvature radii? Possibly you want to check isolated components. Do they meet their specifications? For example, is the pump absorption in your laser crystal as expected? If no discrepancies of that kind are found, then you may ask yourself, was the model possibly oversimplified? For example, did you possibly forget to include ASE in an amplifier despite the high gain? Well, if you worked well before, using competent support possibly, this is relatively unlikely. Let me spend a few words more on discrepancies. You should note that a disagreement between experiment and simulation does not necessarily mean that your model failed. An error in the model, for example some overlooked effect, some wrong data, or just a stupid mistake, might have caused a discrepancy. Often, however, the optical components are just not as you expected, because the vendor may have violated the specifications, or a component may have been damaged or made dirty. You may also simply have mixed up some components. In other cases, the setup may not be properly aligned, or something is wrong with electronic drivers. In any case, keep in mind learning about a discrepancy as soon as possible is useful. Well, in principle you could try to design your prototype laser without a model, but I tell you, you would be likely to encounter various problems. For example, you may find in the experiments that some components need to be exchanged. For example, you need pump diodes with more power to get enough out. Then you have to order new components, spend more money, possibly not use the old components anymore, and of course you wait for delivery again before you can continue your experiments. In experiments you may damage components, for example if excessive optical intensities occur which you didn't think about. Then you have to order replacements, possibly modify the design, etc. If some problem occurs, for example unstable pulse generation in a mode-locked laser, it may actually be very difficult in an experiment to find the cause and to fix it. There can after all be many different possible causes, and each one may require different countermeasures. Indeed, seemingly never-ending problems are not uncommon. A very good thing about a computer model is that it supports you very much in testing potential design changes. A first advantage is you do not need to order new components and test them in the lab. Order only later on what can really be expected to work based on the model. If your design doesn't work as expected, you will quickly find out why and how to correct your decisions. Failed experiments, in comparison, are far more difficult to correctly explain. Another important thing, a change of performance observed in a model can never result from misalignment, dirt, component damage, changed lab temperature, etc. You can be sure that nothing in the model changed if you did not change it. So you get conclusive results where you see change X caused change Y in the result and nothing else. And if your design change hasn't worked as you liked, you can easily go back. No tedious rebuilding as it would be in experiments. So you can avoid wasting a lot of time and money. You just work with understanding instead of doing a blind flight. Now, even if your prototype works well, some further revisions of your design may be required. For example, your boss or your customer wants even more performance. Some tolerances, for example for misalignment, may turn out to be too strict in the experiment. You may want to work with fewer or cheaper components. Again, the model will greatly help you in refining your design. you will understand the effect of each design change without doing expensive, time-consuming and possibly misleading experiments. You can also use it for troubleshooting. If a device doesn't work as it should, you may often see several possible reasons for that. Depending on what it really is, you need to take different actions. Now again, with a computer model, you can check many things quite efficiently. For example, you can check whether a certain effect which you previously neglected might really be strong enough to explain your problem. You can also check, would the use of a modified component cure the problem? If the model says no, it wouldn't, then of course you don't need to order anything and try it out in the lab. Another question might be, how sensitive are certain parameters? Would some design work only if you align components with an extremely high precision? A very important point is that by working with a computer model, you effectively build up your technical competence. Technical competence, of course, implies a qualitative and quantitative understanding of what happens inside your devices. Now, modeling turns your attention to exactly that, much more than experimenting. You may actually have built 1,000 lasers in the lab without ever seeing what causes certain phenomena. You also want to identify fundamental limitations and unavoidable trade-offs. And that is of course achieved with thinking when playing with a model, and not with building or measuring. Also, you can learn a lot from trying out many ideas. A computer model now supports you. It makes such attempts very quick, safe and cheap. Note, you would hardly, for example, invest hours into rearranging a real laser setup and realigning it just for curiosity. I have mentioned a keyword which is very important: new ideas. You may hope that you just go to bed and next morning you will wake up with a great new idea for a design improvement, a new product or whatever. However, you know, normally it doesn't work like that. In reality, new ideas often emerge only after you have focused your mind on various things. For example, if you investigated some nasty effects with a model, if you realized the fundamental reason for some limitation, or if you noticed a remarkable pattern when comparing designs. New ideas are really more likely to emerge when working with models, since that means dealing with what is going on inside. And I don't have to tell you why new ideas are so important in commercial laser development as well as in scientific work. Let us draw a few conclusions. A thorough understanding of what happens inside your lasers is not just nice to have, it is rather indispensable for efficient work. Computer models for laser devices can be used as powerful tools for acquiring such a thorough understanding, essentially by realizing the transparent laser. Working based on blind flight, trial and error in the lab, etc. is wasteful and unprofessional if you have an alternative. The use of computer models costs some money and time, but it easily saves a multiple of what it costs. Therefore, the question is actually not whether you can afford to invest into computer modeling for laser development, but whether you can afford not to do it. Despite of all these arguments, there are some common concerns. A first one is, won't modeling actually be too difficult for me, or at least take too much time? Well, that might be, but what if the alternative means fishing in the dark, never understanding how things really work, wasting time and resources, etc.? In that situation you should not resign, but rather you should think as follows. The first question should be, what is the more efficient approach for your development project? Is it working with a computer model, or is it trying without a model and its benefits? Of course, This depends on the circumstances. There are some cases where modeling doesn't work for some reason. But if the answer is that modeling is required, the next question should be, who should do it? Maybe you can do it yourself. Maybe a colleague of you is better placed to take over this job. Or you could use a competent technical consultant, like me, ask RP Photonics, in order to get the benefits of modeling without doing it yourself. But always keep in mind that if you want to dig into it yourself and buy some high-quality modeling software, this will come with competent technical support. Because if it doesn't come with technical support, then it is simply not a high-quality offer. If you go for RP Photonics, for example, support means general technical consultancy in that area, and that means whatever you try with the models, you are not let alone. A second concern: how can I know that my models will be realistic? Well, models can indeed be unrealistic. For example, if they are oversimplified. However, if you develop them with care, possibly using competent technical support from the software developer, you shouldn't have a problem there. If you find any discrepancies, be happy. Don't consider these as accidents. After all, discrepancies mean that you can learn something which is very often useful. For example, that certain components are not what you thought they are, or that certain effects are more important than you believed. A third concern could be, how can I know that the software works correctly and the components' data are correct? Of course, you need a software which you can trust. Ideally, you know that it has been developed by a trustworthy expert with proven competence. You can, and actually you should, build confidence by first analyzing and testing simpler configurations before you go to more complicated ones. Now, inaccuracies of component data are indeed not uncommon. However, note that not working with a computer model would not simply remove that problem. Often a computer model can actually help you to check component data and to obtain more accurate data sets, or to find laser designs which react less sensitively to variations of certain parameters. If you have now decided that you want to stop a blind flight in laser development and start making your development efficient and faster, you can move forward as follows. First, you could identify the most important technical areas depending on what exactly you are developing. For example, it could be laser resonator design, it could be laser dynamics, for example in the context of Q switching or pulse amplification, or it might be ultra-short pulse generation in the context of mode-locked lasers, ultra-fast amplifier systems and the like. Then think about what exactly you would like to make transparent there, and what kind of questions you would like to answer in order to make faster progress. If you want to get into modeling yourself, try to find out which supplier is most likely to provide suitable, powerful simulation and design software, and also competent, helpful technical support. But if you consider that approach as not efficient in your case, simply find out which technical consultant is most likely to provide competent and reliable technical advice. Of course, that consultant should then have such software and be familiar with it. Well, admittedly here I am biased, but nevertheless consider to contact RP Photonics, whether it concerns software or technical consultancy. I hope very much that you enjoyed this presentation and that it was useful for you.